Yanen discusses the path to AGI, artificial general intelligence, and envisions how AI assistants might evolve, focusing on the architectures and timelines needed to reach that level.
Okay, so I'm going to talk about human-level AI, or how do we get there, and how we are not going to get there as well. So first of all, we do need human-level AI because there is a future in which most of us will be wearing smart glasses or wearing other types of devices, and we'll be talking to them, and those systems will host assistants, maybe not just one, maybe a whole collection of them. And what that will cause is that all of us will have basically a staff of kind of smart virtual people working for us. So it's like everybody would be a boss.
He highlights missing features for advanced machine intelligence, such as persistent memory, that future super-intelligent systems will require. These foundational elements go far beyond what current AI models can do.
Just not of real humans. And we need to build this for basically amplifying human intelligence and, making people more creative, more productive, and everything. But for this, we need machines that understand the world, they can remember things, that have intuition, have common sense, things that can reason and plan to the same level as humans. And despite what you might have heard from some of the most enthusiastic people, current AI systems are not capable of any of this. So that's what we need, systems that learn to basically model the world, have mental models of how the world works. And every animal has one such model. Your cat certainly has one that's more sophisticated than any AI system ever built or ever devised. Systems that have persistent memory, which current LLMs don't have. Systems that can plan complex action sequences, which is not possible with LLMs today. And systems that are controllable and safe. So I'm going to be proposing an architecture for this that I call objective-driven AI. I wrote kind of a vision paper about this that I posted about 2 years ago. And a lot of people at FAIR are basically working towards implementing that plan. FAIR used to have a combination of kind of long-term blue sky research and kind of more applied projects. But Meta, a year and a half ago, created a product division called Gen AI, focused on AI products. And they do applied R&D, so now FAIR has been sort of redirected towards the longer term, next generation AI system. We don't do LLMs, basically.
Addressing Moravec's paradox, he notes how tasks that are easy for humans are hard for computers, and vice versa. Solving this will require new approaches, rather than just refining existing methods.
And we're still missing something big to reach human-level intelligence. And I'm not necessarily talking about human-level intelligence here, but even your cat or your dog can do amazing feats that are still completely out of reach of current AI systems. How is it that any 10-year-old can learn to clear up the dinner table and fill up the dishwasher? And the 10-year-old can learn this in one shot, right? There's no need to practice or anything. 17-year-old can learn to drive a car in about 20 hours of practice. We still don't have level 5 self-driving cars. And we certainly don't have household robots that can clear up the dinner table and fill up the dishwasher. So we're really missing something big, right? Otherwise, we would be able to do those things with AI systems. So we keep bumping into this thing called the Moravec paradox, which is that things that appear trivial to us, that we don't even consider intelligent, seem to be really, really difficult to do with machines. But like high-level, complex, abstract thinking, like manipulating language, seems to be easy for machines, or things like playing chess and Go and stuff like that. Okay, so maybe one reason for this is the following. An LLM is typically trained on 20 trillion tokens. A token is basically is like 3/4 of a word on average for a typical language. So that's 1.5 10 to the 13 words. Each token is about 3 bytes, typically. So that's 6 10 to the 13 bytes. It would take, on the order of a few 100,000 years for any of us to read through this, right? That's the totality of all the text available publicly on the internet, essentially. But then consider a human child. A human child, a 4-year-old, has been awake a total of 16,000 hours, which, by the way, is 30 minutes of YouTube upload. We have 2 million optical nerve fibers, optic nerve fibers coming to our brain. Each fiber roughly carries about 1 byte per second. Maybe it's 1/2 byte per second. Some estimate has said it's like 3 bits per second. Doesn't matter, it's an order of magnitude. So that data volume is about 10 to the 14 bytes. Roughly the same order of magnitude as the LLM. So in 4 years, a child has seen as much visual data as the biggest LLM trained on the entire publicly available text on the internet. So that tells you a number of things. That tells you, first, that we're never going to reach anything close to human-level intelligence by just training on text. That's just not going to happen. Then the counter-argument is, OK, but visual information is very redundant. So first of all, this 1 byte per second per optic nerve fiber, that's already a 100-to-1 compression ratio compared to the photosensors you have in your retina. We have on the order of 60 to 100 million photosensors in our retina, and that gets compressed using neurons in front of your retina to 1 million nerve fibers. So there is already a 100-to-1 compression. Then it gets to the brain, and then it's expanded by a factor of 50 or something like that. So I'm measuring compressed information, but it's still very redundant. And redundancy actually is what self-supervised learning requires. Self-supervised learning will only learn something useful from redundant data. If the data is highly compressed, which means it's completely random, you can't learn anything. You need redundancy to be able to learn anything. You need to learn the underlying structure of the data. So we're going to have to train systems to learn common sense and physical intuition by basically watching videos or by living in the real world.
Yannen emphasizes how humans process vast amounts of real-world data daily, outperforming even large language models in certain ways. He then introduces objective-driven AI, an approach that imagines future scenarios and makes plans, more like human reasoning than simply predicting the next word. He also mentions Meta's open-source VGIA architecture, designed to help AI learn efficiently without millions of trials.
These require thousands of examples and hours of training to learn a single concept. The goal with JEPAs, which means Joint Embedding Predictive Architectures, is to create highly intelligent machines that can learn as efficiently as humans. VJEPA is pre-trained on video data, allowing it to efficiently learn concepts about the physical world, similar to how a baby learns by observing its parents. It's able to learn new concepts and solve new tasks using only a few examples without full fine-tuning. VJEPA is a non-generative model that learns by predicting missing or masked parts of a video in an abstract representation space. Unlike generative approaches that try and fill in every missing pixel, VJEPA has the flexibility to discard irrelevant information, which leads to more efficient training. To allow our fellow researchers to build upon this work, we're publicly releasing VJEPA. We believe this work is another important step in the journey towards AI that's able to understand the world, plan, reason, predict, and accomplish complex tasks.
You cannot predict which word is going to follow a sequence of words, but you can produce a probability distribution of all possible words in a dictionary. But when it's video frames, we do not have a good way to represent probability distributions over video frames. And in fact, the task is completely impossible. Like if I take a video of this room, right? I take a camera, I shoot that part, and then I stop the video and I ask the system to predict what's next in the video. It might predict that there's going to be the rest of the room. At some point, there's going to be a wall. There's going to be people sitting. The density is probably going to be similar to what's on the left. But it cannot possibly predict at the pixel level what all of you look like, what the texture of the wall looks like. And the precise size of the room and all things like that. There's no way you can predict all those details accurately. So the solution to this is what I call joint embedding predictive architectures. And the idea is to just give up on predicting pixels. Instead of predicting pixels, let's learn a representation, an abstract representation of what goes on in the world, and then predict in that representation space. Okay, so that's the architecture, joint embedding predictive architecture. There's two embeddings. Take X, the corrupted version, run it through an encoder. Take Y, run it through an encoder. And then train the system to predict the representation of Y from the representation of X. Now the question is how you do this, because if you just train a system like this using gradient descent backpropagation to minimize the prediction error, it's going to collapse. It's going to say, it's going to learn a representation that is constant, and now it becomes super easy to predict, but it's not informative. But that's the difference that I want you to remember, the difference between generative architectures that try to reconstruct predictors, autoencoders, generative architectures, masked autoencoders, whatever, and then the joint embedding architecture where you make predictions in representation space. The future, I think, is in those joint embedding architecture. We have tons of empirical evidence that to learn good representations of images, the best way to do it is to use those joint embedding architectures. All attempts at trying to learn representation of images using reconstruction are bad. They don't work very well. And there were huge projects on this and claims that they work, but they really don't. The best performance are obtained with.
He also mentions MITA's open source VGIA architecture, designed to help AI learn efficiently without millions of trials. He then speculates on the impact once truly advanced AI arrives. Yan Lin, known for his skepticism, warns that while it won't happen overnight, we should expect profound changes when it does.
If we succeed in doing this, okay, we're going to have systems that really will mediate all of our interaction with the digital world. They will answer all of our questions. They will be with us at all times. They will basically constitute a repository of all human knowledge. And this feels like an infrastructure kind of thing, like the internet, right? It's not like a product. It's more like an infrastructure. These AI platforms must be open source. I don't need to convince anybody from IBM here, because IBM and Meta are part of something called the AI Alliance, which promotes open source AI platforms. But, and I really thank Dario for spearheading this, and everybody at IBM. So we need those platforms to be open source because we need those AI systems to be diverse. We need them to understand all languages in the world, all cultures, all value systems. And you're not going to get that out of a single assistant produced by a company on the West Coast or the East Coast of the US. This will have to be contributions from the entire world. And of course, it's very expensive to train a foundation model, so only a few companies can do this. So if those companies like Meta can provide those base model in open source, then the entire world can fine-tune them for their own purpose. So that's kind of the philosophy that Meta has adopted, and IBM as well. So open source AI is not just a good idea, it's necessary for cultural diversity, perhaps even the preservation of democracy. Training and fine-tuning will be crowdsourced or will be done by the ecosystem of startups and other companies. And this is really what has jump-started the ecosystem of AI startups, is the availability of those open source AI models. How long is it going to take to reach human level AI? I don't know. Could be years to decades. There's a huge variance. And there's many problems to solve on the way, and it's probably almost certainly harder than we think. It's not going to happen in one day. It's going to be like progressive evolution. So it's not like one day we're going to discover the secret to AGI and we're going to turn on a machine and immediately we'll have super intelligence and all of us will be killed by a super intelligent system. No, it's not happening this way. Machines will surpass human intelligence, but they will be under our control because they will be objective driven. We give them goals and they fulfill those goals. It's just like many of us here are leaders in industry or academia or whatever. We work with people who are smarter than us. I certainly do. There's a lot of people working with me who are smarter than me. Doesn't mean they want to dominate or take over.
Concluding, he suggests AGI isn't imminent, but also not impossible. Experts' estimates for AGI range from a few years to a decade or more, reflecting the uncertainty in AI's future.